Lesson 8.5, writing and graphing exponential growth functions. This is kind of where we've been going with exponents. The point of mathematics is to model a world where sometimes it lines up nice and linear, flat line, straight line. Most of the time it doesn't. And there's a lot of mathematics that model things that grow exponentially. They grow very fast, and I'll show you a graph of that in a moment. Or they decay in a similar manner. So what's a linear function? Well, it's easy. It's got the word line in it. So it's anything that's a straight line, any kind of straight line. And that's why we call it that. We've spent most of our time, and you spent most of your time in mathematics at this point, working on linear functions. What's an exponential function? Well, could be exponentially growing, which looks like this. And populations are supposed to grow exponentially. They don't always. The more people there are, the more people have babies. The more babies they have, the more babies they have. So you have some people, and then it grows and grows and grows exponentially. It's actually not working out that way in a lot of chunks of the world, but that's okay. Other places it is. And then there's also exponential decay, which looks like this. And there are a lot of things. Nuclear material, just as one example, decays, so that the more nuclear material there is, the faster it decays up here. And then as it decays, it becomes other stuff, not as nuclear radioactively, not as radioactive as the original stuff, so it decays slower as it gets older and older. So we call it that because it's actually of the form y equals a times b to the x. An example would be y equals 4 times 7 to the x. So these are constants. And this is a variable. So that's what I just said for that one. Let's graph one. We'll use a t-chart. For most t-charts for exponential, I'm only going to use 3 values, but today we're going to use 5. So 2 to the negative 2, well, we know that's just 1 over 2 squared, which is 1/4, also known as 0.25. Negative 1 is just 2 to the negative first, which is 1/2, also known as 0.5. 2 to the 0, as we know, anything to 0 is 1. And that's actually important to know that. We'll use that shortly. 2 to the 1 is just 2. And 2 squared is 4. So we graph it and we get this. Out at negative 2, we're at 0.25. At negative 1, we're at 0.5, then 1, then 2, then 4. And that's what we call exponential growth. It starts getting bigger slowly, and then it just takes off. Never goes below 0. So you can put any number in. So your domain means all reals. Any number can go into that. It won't blow up your calculator. You can put a negative number in, you can put 0 in, you can put a positive number in. But no matter how hard you try, you're never going to get 0 to pop out of that function or anything negative for this particular function. So for the range, we'll just say y is always greater than, not greater than or equal, but always greater than 0. So as you can see down here, it keeps getting closer and closer and closer and closer and smaller and smaller. 0.5, 0.25, 0.125, point so on and so on and so on. It just gets smaller and smaller. It never actually hits. Domain and range are up there. So, like I said, I'm only going to use 3 numbers now. So we'll do this one. -1, 0, 1. 2 to the negative first is 1/2. 3 over 2 is 3/2. 0 is 1, so we get 3. 1 is 2, we get 6. So at -1, we're here. At 0, we're here. And at 1, we're 6 here. So I'm going to guess that since all exponential functions look pretty much the same, it's going to do this. That's y equals 3 times 2 to the x. If I was to graph y equals 2x, 2 to the x, actually I'll leave it in red for the t-chart. -1, 0, 1. 2 to the -1 is 0.512. So I'll put this in green. -1 is going to be here. 0 is going to be here. 1 is going to be here. So this one's going to take off, but not as fast as the other one. So when we put this coefficient out front, just makes it, we call it stretching it vertically. It just makes it kind of move up at a faster rate. And then this one, we'll do all in purple. Y equals -3 times 2 to the x. The negative makes it flip down, but we'll find out. -1, 0, 1. 2 to the -1 is 1/2, so that gives us -3/2. 0, 2 to the 0 is 1, that gives us -3. And 2 to the 1 is 2, that gives us -6. So it'll be just like the blue one, except flip down. So the mirror image down. That one goes here. This one goes here. And this one goes here. So some practice in graphing. You can always put this in your calculator to check, but I recommend getting good at it without the calculator because you never know when you're not going to have a calculator. It helps you understand a little bit better than just punching things blindly into your calculator. So this is an exponential function. I kind of need to tell you that. You aren't good enough yet to look at it and say, I've got it. Here's the way you know it's an exponential function. How do you get from 3 to 9? I'll multiply by 3. How do I get from 9 to 27? Same thing. Same thing. Same thing. Therefore, it's an exponential function. And this times 3 is your b value. So once you see that, you say, well, that's my b value. B equals 3. Then you go and you pluck out where the 0 is because you're looking for y equals a times b to the x. And if I know that when x is 0, I get b to the 0, y equals a, because b to the 0 is 1, then 27 equals a. And I'm looking at y equals 27 times 3 to the x. There's my equation. Scrolling a little quick there. So try it again. And I recommend trying it on your own here with your notes out front. I'll give you a second to get ahead of me. Or you might want to pause the video. That's my b value. That's my a value. Equation is y equals 8 times 2 to the x. Cool stuff. You can always check by putting values in to see if that makes sense. So if -2 is here, 2 to -2 is 1 over 2 squared is 1/4 times 8 is 2. Looks like it worked. So last thing, this is where we get exponential growth. When you put money in the bank, it grows exponentially. Unfortunately, the interest rates are so small. For example, interest rates these days are ridiculously called 1%. I could put $1,000 in and leave it there for 10 years. And it's not going anywhere. We just plug it in here. A is the amount. In this case, $1,000. R is the rate. T is the time. So 1 plus 0.01 to the 10th. Y equals, and I need a calculator, which I don't have handy. So for those that haven't seen it, you can go 1.01 power to the 10th, and I multiply by 1,000. I'll have $1,104. So the reward I get for not touching my $1,000 for 10 whole years is to make $100 and $104 in interest. Not really much to make that incentive happen. That's it. Good luck. Exponential functions aren't too bad, and we're also going to practice them in the next lesson where we get negative, what we call exponential decay.